Um, once more, good evening. Today, we're going to sort of refresh a little bit more on how to apply hypothesis testing to two populations. We already did that, but when I looked at the homework assignments submitted by some students, a few students, when they reject the null hypothesis that two subpopulations have the same average, when they reject that null hypothesis, they reach the conclusion that there is no significant difference between the two populations. As a matter of fact, that is the opposite of the conclusion. When you reject the null hypothesis of equality, you are now concluding that there is no equality. That's what it is. Because there are two hypotheses here, the null and the alternate. The null hypothesis says that two subpopulations are the same. The averages of some measure are the same. The average age of houses in two neighborhoods. The average of male and female students is equal. That is your null hypothesis. The alternate hypothesis is that the average age of females is not equal to the average age of males. And so once you reject the null hypothesis, which says the average age of females is equal to average age of males, then you are concluding that the average age of the two groups are not the same, okay? And I'm going to go back and refresh a little bit on that, maybe in about 5 minutes. And then we get into ANOVA, the analysis of variance, which looks at comparing the average between 3 or more populations, okay? We use a different statistic. When we conduct that hypothesis, we use what you call an F statistics, F as in Frank. And then our hypothesis is that all the averages are equal. And the alternate is that there must be one group among the 3 or more that does not have the same average as others. Once we reject the null hypothesis of equality and conclude that there's at least one group that is not equal to the others, then we go through what is called a post hoc test, post hoc, H-O-C, a post hoc test, which the objective is to find out which two groups are not the same. Suppose you are testing 5 separate groups, and you say that the averages of all the 5 groups are the same. It could be that 1 and 2 are the same, but 1 and 3 and 1 and 4 and 1 and 5 are not the same, okay? It could just be that there's one that is not the same as others. All right. So let's get on with it. I'm going to pull up, I'm going to share with you some slides. And I'll use those slides to make the point or to illustrate the points. All right, so let's begin with the hypothesis test for two populations. And after I do the illustration, I'll go to your homework assignment and use that also for an illustration. All right. Can you see my screen?
Yes.
Yes.
Okay. Thank you very much. All right. So now I'm going to illustrate the test of hypothesis for two populations. I mean, you can use disease statistic and compare the calculated Z with the critical Z. But here, the issue that I found out from homework assignments that I graded was the interpretation of the confidence interval as a means of hypothesis testing. Now, confidence interval has its purpose. You're simply trying to estimate the mean. That's what you're trying to say. You're trying to estimate the mean and come up with an upper level and a lower level. You say the mean, the true mean, falls between these two ranges, and that's perfectly fine. That is one purpose. But the point is that you can stretch that purpose to hypothesis testing, which has its own methodology. Okay. And our objective, like in this particular illustration, is to compare the ages, the average age of houses into the average age of houses in two neighborhoods. Okay. Because what you're really comparing is the averages, the true population average you are looking at. Okay. And the problem, as I said, is that we have a population of houses in a neighborhood. That is the problem. We have a population of houses in a neighborhood. Actually, that is the subject. The subject is that we have a population of houses. This population of houses is what you're looking at. You are trying to look at some of their characteristics. It could be the average age. It could be the average size. It could be the average lot on which the size of the average lot on which they were built. It could be a number of other parameters. Okay. And we only have a sample. An objective is to use information from the sample to reach a conclusion about the true population. Okay. And so we then proceed from there. The problem, this is your problem. Okay. This is the real problem here. Okay. All right. And of course, as we said the last time, we collect a sample of houses, size n, could be 50, could be 100, could be 200, and then calculate the sample mean, calculate the sample standard deviation, and we state a level of confidence, 98%. Okay, or we can state a level of significance, which would be 2% in this case. And once we select a confidence level, we determine the critical Z value for that level of confidence. In this case, is 2.33. And most students, practically every student, was able to identify the critical Z value, right? And so we calculate a sample mean, which is 64.0, and a sample standard deviation, which is 22.6. The sample size in this case was 31. And so the confidence interval is given below. Which is the sample mean minus Z times sigma over root n. And let me make that clear because a few students did not exactly know that you have to calculate this inside part first, and then you subtract it from the sample mean. So let's do the same here. Okay. All right. So once you have that formula set up, this is the calculation. Okay. And the sample mean ranges from the possibility of 55.4 to a high of 74.634. And so you don't know what the true mean is, but you are 98% confident that it is between 55.4 and 74.6. All right. So the problem we're looking at here is we look at two populations, okay? Houses that have a pool and houses that have no pool. We are going to compare the average price of the two types of houses. Houses that have a pool and houses that have no pool. Okay. The null hypothesis is simply that the average sizes of the houses or the average price of the houses, any parameter here, are equal. And now, if the average of one group is equal to the average of the other group, then the two averages, if you take group 1 minus group 2, or the average of group 1 minus the average of group 2, what you get is a 0. If two numbers are equal, then if you subtract them, you get a 0. And so you say there is no significant difference in the average price of houses. Okay? In average price of houses. Now, if there is a significant difference, then mu1 minus mu2 will be equal to 0. So there is a significant difference in the average price of houses. Right? So we'll go through the calculation that we know already. And so this is the calculated Z, that is the critical Z. And so you state your level of significance. And so you have the sample mean. This is the sample mean. And that is the sample standard deviation here. And so there is 38 in sample 1, that's 67 in sample 2. So then you go through the calculation and you use the absolute value to make your decision, calculation and decision rule. So your calculated Z, and I'm going to call this calculated Z, is 3.477. And so if Z is greater than Z star, you reject the null hypothesis. And since the calculated Z, 3.477, is greater than the critical Z, you reject the null hypothesis that the average prices are the same. Okay? And so you conclude that the average prices are not the same. Now, what happened then is that you can use a software to calculate the critical value. As you can see here, the critical value is the same as we had when we did the calculation by hand. This is a software, this is SPSS. And so we get the same 3.477. Remember, I said use the absolute value, which means you have to ignore the sign. But what happens is that if you do a confidence interval, instead of calculating doing a calculated Z, if you use a confidence interval, as I explained last time, if you have two negatives in the confidence interval, that means you have to reject the null hypothesis of equality. If you have two negatives or two positives in the lower and upper values, then you must reject the null hypothesis of equality, okay? But if you go from positive to negative, then you are not able to reject the null hypothesis. I want to make this very, very clear because once you are not able to reject the null hypothesis, you are saying that the two averages are equal. If you reject the null hypothesis, you are saying that the two averages are not equal. That's very simple, okay? Does anybody have any questions on that explanation? Hello?
No.
Okay, fine.
Nope.
So somebody has spoken for everybody. So now I'm going to go to the next topic. The next topic,
Professor.
yes.
Are you able to like type that out? Like if it's not positive in both upper intervals, lower and upper is rejected.
Okay, I'm going to create a new slide. Okay. I'm going to say confidence interval and decision and hypothesis test. Let me say confidence interval and hypothesis test. From SBSS. Okay? If the confidence interval of the difference, this is what you're going to see, okay? There's two negative numbers on the upper and lower values. That means you must reject the null hypothesis of equality and conclude that the averages are not equal. Okay? So once you have the confidence interval of the difference shows two negative numbers or two positive numbers. Okay? Must reject the null hypothesis. All right. So if the confidence interval of the difference is mixed, positive and negative, then we cannot reject the null. All right, I'm going to reduce this a little bit. Okay, so you cannot reject the null. So this means that the averages are equal. So that makes it very simple. And once you read off the printout or the results from any software, that's what I'm going to give you. I'm going to give you either two positives or two negatives, which means you reject the null hypothesis. Or if you have the mixed positive and negative values, then you cannot reject the null hypothesis. And therefore, the averages are equal. Is it clearer now?
Yes, Professor.
Yes.
I have a question.
Sure.
So for the level of significance for my homework, I chose 5%.
Fine.
The answer that I should have got should have still come out the same as if I would have chosen 2%, right?
No, if you choose 2%, you're being more conservative.
Okay.
Okay. For example, if you go to a 5% level of significance, you might reject the null hypothesis of non-equality if you're doing two populations, or let me put it this way, if you do a 5%, you might reject the null hypothesis. But if you try to go to, say, a 1% from a 5%, or even from a 5% to a 2%, you might not be able to reject the null hypothesis. But because realize that the level of confidence that you select, or the level of significance, essentially indicates how conservative you want to be. That's the chances that you could be wrong. Because if you say you want to say, let's go to the extreme. Suppose you want to go to a 100% level of significance, which means you are actually trying to say that you couldn't be wrong. Then in all likelihood, you will not be able to reject an hypothesis because you can never be 100% confident if you're using a sample. So if you now take the position that you just want to take a 1% chance of being wrong, then you increase the likelihood that you will not be able to reject your null hypothesis. I often ask students a very simple question. If you are doing a hypothesis test, suppose that you and your friend or your cousin want to estimate the possible average attendance at a block party, okay? And you want to invest money in it. You could be estimating with a 10% level of significance or a 90% confidence level. That's a 10% chance you could be wrong. And then I ask students, what if you are building an airplane? What level of confidence are you going to take? Why is it that pilots will take a 99.9999999 up to 59s level of confidence? And so the level of confidence that you choose or the level of significance that you choose depends on what you are addressing. If you're building a Boeing 747, you're going to take a 99.99999 all the way. And in fact, it becomes relevant when you're trying to build a Boeing 747 for the simple reason, one, there's a lot of money involved. This is number one. Your whole career is involved. There's human life that's involved. When you choose the 99.9999959's confidence level, it does not mean that you're going to be right all the time. No, there is still a one chance in a million that you could be wrong. Okay, something could go wrong. Okay, so if you go from a 5% confidence level, significance level to a 1% significance level, chances are you will not be able to reject the null hypothesis. So at least the chances get higher that you will not be able to reject the null hypothesis. Because, I have tested things at half of 1%, 99.5% confidence level, and I'm still not able to reject the null hypothesis. Excuse me, and I'm still able to reject the null hypothesis. It depends on how consistent the values that the population is. Okay, if everybody is doing the same thing, then suppose we specify houses in a neighborhood that must be 1,500 square feet. And so if you go and do a test of hypothesis that the houses are an average of 1,500 feet, of course, you will have a zero variance. This is number one. Therefore, you not be able to reject the null hypothesis that all the houses are of equal size. Okay, all right. So did I answer your question?
Yes.
All right. So let's now go to the next level. I'm going to pull up the slides. Here, we're going to be looking at test of hypothesis for 3 or more populations. All right. So here we are dealing now with what we call the analysis of variance. We're now going to go through the Gore calculations. We used to do that when we were in the lab teaching this class because we are able to illustrate the point. Now, for analysis of variance, we're actually also trying to test a hypothesis for the equality of means. But instead of testing a null hypothesis that, say, the mean is 75, which is what you do for one population. You're saying the mean is 75. Now, for 2 populations, you're simply saying that the mean of one is equal to the mean of the other one. Okay? You can also take the hypothesis that the mean of 1 is different from the mean of 2 by 10. Okay? So in that case, your null hypothesis would be that mu1 minus mu2 is equal to 10. Okay, but this time now you are testing the equality of means for 3 or more populations. You're testing the null hypothesis for 3 or more populations. In which case, let us say that in this neighborhood, we have 3 kinds of houses. Okay, we have ranch houses, we have Victorian design, we have colonial design. And we're saying the average size or the average age or the average price, whatever variable we want to take, are the same. And so the null hypothesis will be that mu1 is equal to mu2 is equal to mu3 is equal to mu4, as many groups as you want to choose. Okay, that would be the null hypothesis, that all the averages are equal. And then the alternate hypothesis will be that at least there's one pair. Okay, for example, mu1, there's at least say mu1 and mu2 are not equal, but others are equal. Or you can even say that mu1 is not equal to mu2 and not equal to mu3, in which case any two that you pick up, they will not be equal. That is the alternate hypothesis. But at least one, mu3 and mu4 are not equal, but others are equal. Okay, or at least mu3 is different from the other ones, or mu4 is different from the other ones. So that is your alternate hypothesis. Now, instead of using the calculated Z, here we use what we call the F distribution. So we have a calculated F. Instead of a calculated Z or a calculated T, we have a calculated F distribution, all right? This F distribution has what we call 2 different degrees of freedom. Okay, there's a numerator degrees of freedom and a denominator degrees of freedom. All right, so now once we do a test of hypothesis, if we reject the null hypothesis, okay, if we reject the null hypothesis, then we have to find out which of the various populations, which 2 are not the same. All right. All right. So and see here, there are 2 degrees of freedom, the number of populations minus 1, and the sample size minus the number of different populations, all right? And so the smaller degree of freedom is the numerator degree of freedom, which is the number of populations. And the bigger degree of freedom is the sample size, the total sample size now, minus the number of different populations. K is the number of different populations. N is the sample size that we have, the total sample size. Okay. And the F distribution is illustrated here, and I'm going to show it. All right. Okay, you can see here that we have degrees of freedom, the numerator, which is 3, and the denominator, which is 18, and that the critical F here, if you use a F table, the critical F here is 5.09. And so you reject the null hypothesis if the calculated F is greater than 5.09. Suppose you have 3 and 15, the critical F will be 5.42, and so forth and so on. Okay. Generally, when you have the raw data, you're going to have three populations or four populations in this example. The sample sizes need not be the same. Your N will be the sum of the three different samples. Okay, this one has 1, 2, 3, 4, 5, 6. So 6 plus 1, 2, 3, 4, 5, 6, 7 is 13. And then you have 18 and you have 22. So 22 minus 4. 22 minus 4 gives you the 18 degrees of freedom that you see in this table. Okay, N minus K. So there are four different populations, and altogether you have a sample that 22 altogether. Okay, they don't have to be equal sample sizes. So 22 minus 4 gives you 18. And then K minus 1, as 4 minus 1 gives you 3. And that is why we have 3 and 4. Okay, the numerator will be 3 degrees of freedom, and the denominator will be 18 degrees of freedom. So we read off the critical value will be 5.09. Okay, and of course, you choose the
Hey,
level of
Professor, Professor, can you do that one more time? Can you say that one more time?
Okay, say what is that?
The from the 3 degrees numerator and the 18.
Okay, so
Yeah.
let's go back to the sample size. The the numerator is the number of populations minus 1, right? How many populations do we have here? 1, 2, 3, 4. So 4 minus 1 is what?
3.
3. So the numerator degrees of freedom will be 3. Okay. Now you have 1, 2, 3, 4, 5, 6. 6 plus 1, 2, 3, 4, 5, 6, 7. That's 13. Plus 5, that's 18. Plus 4, that's 22. So the denominator degrees of freedom will be N minus K, which is these 22 samples that we have. 22 minus 4 is how many?
18.
18. And so this is why when we come here to choose from the table, we have 3 and 18. 18 denominator and 3 numerator. Usually the F table, has tables for specific levels of significance. And so our level of significance here is 0.05. Okay, 0.05, and I'm going to all right. So we have a 0.05 level of significance, 3 and 18 degrees of freedom, which gives us 5.09. So have we got the 5.09?
Yes.
All right. And the table you will see for the F distribution will have specific levels of confidence, of significance, because the calculation of the F table is a little bit involving. All right. So we're looking at the average age of houses in the same, we're saying that the null hypothesis is that the average age of houses is the same regardless of the style, ranch, two-story, or tri-level. The average age of the houses is the same. And when you're looking at a problem like this, you say, what leads you to this kind of hypothesis in a practical world situation? What would lead you to this kind of hypothesis in a practical world situation will be, for example, that suppose there's a housing development in a neighborhood, and that housing development specifies that you should build different styles for different customers. And so the development all started at the same time, except that different customers chose different styles, and so the average ages would be the same. But suppose Suppose, on the other hand, that the first group of customers that came into the neighborhood were building ranch-style houses. And maybe 5 years later, new customers begin to come and say, some of them don't want the ranch-style houses, some of them want two-story houses. So now you will find out that the average age of two-story houses will be different from the average age of ranch-style houses. And then 7 years later, new customers begin to come in. Some want ranch, some want dry level, and some want two-story. You will see that the average ages of the three types of houses will be different. All right? All right. So your null hypothesis will be that average age of ranch, average age of two-story, and average age of tri-level is the same. The housing development occurred at the same time, and customers simply chose what types of houses that they wanted, but they all came to us about the same time. As new customers come in, they chose different styles. And so the average age of houses will be the same, regardless of the style. The alternate is that at least there is one pair of groups with different average ages of houses. Okay, this is the same thing we talked about. This is the mathematical process. Like I said, we used to go through it. It's quite involving. I want to be honest with you, it's quite involving, but I have examples of it. If you want to see those examples, I will post them online. And so we print a software printout for an ANOVA test, and it will show you the calculated F. As you can see here, the calculated F is 7.49 on the average age of houses, and the living space, the average size of living space in the houses is also tested.
Professor.
Yes.
What is that sig? What does that represent? Where it says 0.001 and in the bottom it says 0.000 on the sig.
Okay. Excellent question. Because it answers your original question. All right? Which I try to explain. Suppose you chose a 5% level of significance. All right? Which is 0.05. You get it? And you might reject the null hypothesis if your level of significance is 0.05. But if you keep increasing, if you keep reducing the level of significance from 0.05 to 0.025 to 0.01 to 0.001, you're going to get to the point where you're not going to be able to reject the null hypothesis. So what the SIG here is saying is, this is how low you have to reduce your level of significance before you're not able to reject it. And therefore, if this SIG value is lower than your chosen level of significance, you must reject the null hypothesis. You get it?
Yes, kind of. How do you calculate that though? Or that calculates on its own when you do the ANOVA test?
There's a way to calculate it, but again, it's an involving mathematical calculation.
Okay, no problem.
It is called a row value. And this is why very often softwares will print it out for you. But once this row value is called a row value, let me see if I can. Okay, something. I mean, ordinary people call it the p-value.
This is row as in correlation?
Yes, it's row as in the Greek row. Okay. The row value. That's what it's called. Let's see if we can reduce that. Okay, that's
But
called the raw value.
got it. But we haven't learned how. Well, I haven't learned how to calculate that, right? Not yet.
No, you have not.
Okay. All right. No problem.
Okay, so you don't have to worry about
Okay.
it. Okay, call the
That's
raw
all
value.
given to us, right?
Huh?
Generally, that the level of significance, which that is, that's usually given to us, right?
As a statistician, you choose your own level of significance. Okay, you choose it. But if I give you a test, I'll give you a level of significance for you to test, because I want to know that you are able to find a critical value. You're able to also calculate your calculated value. You get it?
Yeah, it makes sense.
Okay. All right. So, as in this particular case, we found out that the calculated F 7.49 is greater than the critical F of 5.09. So we reject the null hypothesis that all the average ages are equal. So we reject that null hypothesis. So we are saying there's at least one group among the several groups that has a different average. The average amount of living space is, the F value is 27.03. So you know that you're going to reject the null hypothesis, and it will take quite a bit. Practically, you want to become perfect before you are not able to reject the null hypothesis. And of course, are you surprised that ranch houses and 2-story and 3-story are not going to have the same average amount of living space? You're not surprised, okay?
Professor, quick question.
Yes.
P-value and level of significance, aren't they two different things?
No, they are mirror image. So this simply indicates, like say, the p-value simply indicates to you how far you have to push your level of significance for you not to be able to reject the null hypothesis.
So if it was at 0.01, you will have to reject it?
Now, if, for example, your level of significance is 0.05, right? And the software gives you a calculated p-value of 0.001. 0.001 is less than 0.05, am I correct?
Yes.
Good. So when the p-value is less than your level of significance, then you reject the null hypothesis.
Okay, that makes sense.
Okay? All right. And so, I mean, this is essentially what we have here. We are using 0.01 level of significance, and here the critical value is 4.79 because we have a very big sample size. The denominator degrees of freedom is 105, and so your critical value here is 4.79, but your calculated F is 7.49. So we reject the null hypothesis. So this is our decision here. Our decision is we reject the null hypothesis. We are saying that the average age of houses between ranch, 2-story, and 3-story, the average ages are not the same. We are rejecting that null hypothesis of equal age among them all. And so our next step is to now compare and find out which group is different from the others. And so this is what we call a post hoc test. Okay. Okay. So we're now compare the 3 styles of houses in the neighborhood: tri-level, 2-story, ranch. So we compare tri-level to 2-story and tri-level to ranch. the mean difference is negative, which really doesn't mean anything. The age of houses, if you subtract, if you change the order, this could be positive, but the same number. And so you can see that here we have two negatives. Am I correct?
Yes.
Okay. And we're actually testing at 95% confidence or 0.05 level of significance. And so since we have two negatives, we are saying that we reject the hypothesis that tri-story and two-story, tri-level and two-story are the same age. We are rejecting that null hypothesis. Okay. And so we are concluding that between tri-story and two-story, tri-level and two-story, that the average age of one is more than the average age of the other one. That's of one group. It's more than the average age of the other group, or they are different. But when you compare tri-story, tri-level to ranch, you're going from negative to positive, and therefore you are not able to reject the null hypothesis of equality between those two. So it must be then that between tri-level and two-story, there's a difference. Okay? And here we are comparing ranch to tri-level. And as you can see, we get the same result here, okay? But when you compare ranch to two-story, you can see that you also reject the null hypothesis that ranch and two-story are the same age. So, which groups are different? Ranch is different from two-story, and tri-level is different from two-story. So it must be two-story that is the problem, if you want to call it a problem. The two-story houses are different from the other ones. You get it? Does it make sense? If it doesn't make sense to you, let's see if we can take it again. Hello?
Is it because every time it's matched with the, like, say with tri-level and two-story, it will always reject, and then with ranch.
Yes.
Okay.
You see, because each time we compare two-story to anyone, we reject the null hypothesis of equality.
Right. Okay.
You get it? Because we compare two-story to tri-level here, we reject the null hypothesis of equality. We compare two-story to ranch, we reject the null hypothesis of equality. But when we compare ranch and tri-level, we are not able to reject the null hypothesis of equality. And right here, the same thing, tri-level and ranch. Okay? I mean, I have tested hypotheses like this for 5 groups, for 7 groups. And you really have quite a bit of twisting your brain, but it's not like it's difficult. Okay? I think I'm going to post a project that I did like that many years ago, and you see what I'm trying to say.
Quick question, just a reminder. So for looking at the 95% confidence interval, if we get 2 negatives, that's an automatic reject?
Yes.
Okay.
If you get 2 negatives or 2 positives.
Oh, okay, or 2 positives. Got it. Thank you.
Okay. Once you go from negative to positive, then you're not able to reject the null hypothesis. Okay, this is just the mathematical formula. Like I said, we're not able to illustrate that here because it's a convoluted calculation. It's not really convoluted. It's tedious. It's not convoluted. It is tedious. But when we used to be in the classroom and we were in the lab where you can all practice with me, then we usually would go through the calculation. And everybody will practice it, because once you practice it, it's not like a difficult thing to do. It's just that it is quite tedious. But now you have computer software like SPSS or any statistical software that does that calculation for you fast. If you now want to go and be a theorist in statistics, like like I am, like I got a PhD in it, then it becomes necessary that you know how to calculate it, because you have more complicated problems in the sense that you have more complicated data structures and data configurations that you will need to know how to develop a mathematical process in order to address complicated data configurations. Are we clear? Okay, let's just look at a practical problem from your homework assignment, so that you can navigate the assignment without much trouble. I'm going to pull up another document. I'm hoping that pull up okay. All right, are you able to see my screen?
Yes.
All right. So you are looking at the bank problem that is part of your homework assignment. And it's about a bank that has 4 branches. So you can see here that you have four branches, and you ask yourself a simple questions. Do customers in the 4 branches have the same average amount of balances in their checking account? The average amount of balance in the checking accounts of customers, is it exactly the same or approximately the same for all 4 branches of your bank? Okay. Now you have your F calculation, the calculated F, and you have the SIG, which is the p-value. I'm going to call this p-value so that we can keep things in our heads. We have the p-value at 0.015. And since this p-value is less than your level of significance, of course, you reject the null hypothesis, and you conclude that the average balances for customers is not the same for all branches. So once you have rejected that null hypothesis, and we are testing at 0.015, okay? And so here, you calculate, ask yourself, which of the branches is different? We are looking at Ohio, and we compare Ohio to Georgia, and you see that Ohio to Georgia is different because you are rejecting the null hypothesis of equality between Ohio and Georgia. You see the negative values?
Yes.
Hello?
Yes.
Okay.
Yes.
So in this case, you are saying that Georgia and Ohio are not the same. But when you compare the confidence interval for the other branches, you see that you go from negative to negative. So that means that Ohio and Kentucky and Pennsylvania are the same. Okay. You can see that Ohio and Kentucky is the same, and Ohio and Pennsylvania are the same. Because the confidence interval goes from negative to positive. You get it?
Yes.
All right. Here you're comparing Georgia to Ohio again, which you have done before, and see you get the same result. But again, when you compare Georgia to Kentucky and Georgia to Pennsylvania, you see that you go from negative to positive, and so Georgia and Kentucky are the same, and Georgia and Pennsylvania are the same. So which branch is the culprit here?
Ohio.
Ohio is the culprit that is making them not to be, that is where you have that are equal. I'm sorry, Ohio is the one that is different from the others, okay? Because Georgia and Kentucky are the same, and Georgia and Pennsylvania are the same. And so Ohio is the same as Kentucky, and Ohio is the same as, what do you call it? As Pennsylvania, but Georgia and Ohio are different. As you have here, Georgia and Ohio are different. And so if you keep going, you keep getting the same result. It does not have to be only one that is different. It could be that they're all different from each other. It could be that they're all different from each other. But the reason that you rejected the null hypothesis of equality is because Ohio is different from Georgia. And that makes you reject the null hypothesis that everybody is the same. But once you reject the null hypothesis that everybody is the same, then you begin to ask yourself, who is different? It could be that it's just one, at least one, that is different from the others. It could be like in this case, Ohio is the one that is different from the others. But it could also be that they're all different, totally different from each other. You get it?
Yes.
I have a question.
Okay.
So, seeing from Kentucky and Pennsylvania, you failed to reject the null.
Okay.
How come it's not different there with Ohio?
Okay. I don't get the point here is that Ohio is different from Georgia, right?
Right.
Okay. Ohio is not different from Kentucky. Ohio is not different from Pennsylvania, right? So it's just that Ohio is different from Georgia. Like you see here, Ohio is different from Georgia, but Georgia is the same as Kentucky, and Georgia is the same as Pennsylvania. And so here again, Kentucky is the same as Ohio, which you find out from the beginning here. Ohio and Kentucky are the same. So when you come here, Kentucky versus Ohio, they are the same. Kentucky versus Georgia, they are the same. And so the big issue is that Ohio is different from Georgia.
Oh, okay. I see now. Okay.
You get it?
Yeah, I get it.
Okay. So any other question? All right. In the absence of any further questions, I take it that
Professor, so for the homework, how will we go about answering the questions?
how you go about answering the question is, first of all, you ask yourself whether or not you reject the null hypothesis for equality. If you are not able to reject the null hypothesis of equality, you simply conclude that the averages are the same everywhere. But
Okay.
once you reject the null hypothesis of equality, then you go through this second stage, which is to find out who is different. Essentially, I have answered the question for you.
Okay, so you just want the answer of who to reject and who not to reject?
Yeah, first of all, you have to ask yourself whether you reject the null hypothesis of equality. And once you answer that, if you reject the null hypothesis of equality, then I want you to go to the second stage. Which two are different? Or are they all different from each other?
Okay, makes sense.
It makes sense? All right. Okay, guys. Enjoy your evening.
All right. Have a good night, Professor.
All right.
All right. Have a good night. Good evening.
Well, you too.